All right, here we're going to go. This is chapter 5. It's a little easier than chapter 4, but it uses some of the information out of chapter 4. So I will recommend that you definitely, if you had problems in chapter 4, continue to work on chapter 4, and you'll see what I mean when I talk about certain concepts. So table of contents, work, energy, conservation of energy, and then power. We'll get to those real quick. So first of all, definitions, work. Work is done when an object is changed by a force. So you have to do a force changing or movement of an object. So this is only the case when you're going against a force. Example, when you lift a box up. You are opposing gravity, you lifted the box up, so then force over a distance, you've done work. Now if you take that work and you have that box and you somehow walk with that box, you are not doing any work because the force you're facing is gravity. Your work is that way in the x. The displacement is not against the force, so there's no work done. So work can be positive or negative. Moving on, here's your definitions of power. If you want to pause it for a second, write it down. Two equations, work divided by time, or power equals force times the speed. And you'll see that in the calculations here in a minute. Kinetic energy. All right, back to physical science. Ke, or kinetic energy, is 1/2 times the mass times velocity squared. Please don't forget the squared. It's a common mistake. Kinetic energy, energy of movement. That's why you have speed in the equation. So now we get to work. How does all this tie together? Work equals a change in kinetic energy. So we have to find the net work to find the change in kinetic energy. Now you ask, how is all of that related? Well, example. So now we have the coefficient of friction. We give an initial speed and an initial mass. We know the coefficient of kinetic friction is 0.1. So now we have to put all chapter 4 and chapter 5 together. There's the stuff we were given. Notice that work equals force times distance times an angle. Work net, friction times the distance times the cosine of angle. Mu of k times mass times gravity. Again, this is for a sled on a flat surface. The force due to gravity is what F of n is, and that's why it's mass times gravity right there. So, to solve it, it's a big algebra problem, and we'll do this again in class. I would take your time and read through it to understand why we do it. It should be good to go. So, you substitute everything in, the distance is 2.5. Not going to worry about that one. So, potential energy. Energy is associated with a shape, a position, or a condition of the object itself. So, example, position. You take a pot and you put it up very high. Well, guess what? That's got potential energy. As it starts to fall, it'll change to kinetic energy. Specifically, a gravitational potential energy is that pot sitting on that shelf. Okay? So you have potential energy, gravitational fields. We will not play with gravitational fields at all. But if you notice the equation, potential energy due to gravity is mass times gravity times height. I will tell you on the subscripts, if you keep it potential energy of gravity, or PE sub g, equals mass times gravity times height, it will be kind of convenient. It will help you later on. Great, that video didn't show. Now, there's elastic potential energy. This is of springs, of stretching things out, of deforming some things. So potential energy elastic, potential energy E, I don't know why they just didn't say PEE, equals 1/2 times K, which is your spring constant, which is how stretchy this thing is. And the distance is either stretched or compressed. And it should make sense because if you take a rubber band, you stretch it out, great. Or you can take something and smash it down. Take a piece of rubber, you smash it down. A tire, smash it down. It's going to want to bounce back. There's a spring constant. Use letter K, kind of is that measurement. Example, look at there. There's a picture of it. So if it is relaxed and then we smash it down, it's compressed. And so we have the distance compressed. That would be the x in our equation. So what I would recommend is I'm going to have you write all this down, and we're actually going to do this in class. But if you take a second and write it down, it'll speed up class a lot. All right, good enough. Because I'm not going to go through it here. I'm going to go through it next in class. Okay, section 2. Basically, you have to sit there and say everything is conserved. So, example for energy, we can't just say, oh, look, I have potential energy, and it drops to kinetic energy. It's got to transfer somehow. In theory, it would be great if all the potential energy went into kinetic energy. Or even yet, oh, wait, when you use electricity out of the wall, the energy you're getting should be converted to what you're trying to do. In a perfect world, you turn on a light, all that energy is converted to light. Guess what? It doesn't. If you haven't figured it out, light bulbs get hot, they heat up. Wires get hot, they heat up. You're losing some of that energy. How does that relate? You have to have a total amount of energy. In this case, mechanical energy. So we're talking about things moving. Mechanical form is kinetic plus potential. Okay? And then again, you'll see all forms of potential energy. Mechanical energy initially is equal to mechanical energy final. That's just saying the common sense answer. If I have this much energy, I should have this much energy when I end. It should be the same number. So, mechanical energy here, they always use a clock. I think it's kind of funny. In the bottom, when the bottom is, you pull it back all the way to the left, you have all potential energy. There's no motion. You let go, slowly as it comes down at the very bottom, it's moving, it's fast, cool, it's all kinetic energy moving. And as it goes back up, it starts to lose speed, kinetic energy, change it to position, potential energy. The very top, again, off to the right, in that case, you have all potential, and it just keeps going back and forth. Does it go forever? No, you lose some as friction. Guess what? You still can calculate it. All right. Frictionless slide, woohoo! We'll actually go through this one in class. I want to get to the concepts. Mechanical energy. Friction will be our stumbling block for energy. We won't do it initially, but I will tell you right now, we will be able to calculate how much energy is lost, depending on what situation it is, and we'll get through there. You might want to watch this one more time. Make certain you have notes ready. If you have questions understanding the theory, we'll talk about those first, briefly, real quick, and then we'll go into the calculations. This, again, should be easier than Chapter 4, but depending on how bad Chapter 4 went for you, that might not be a great thing. Anyway, if you aren't good on Chapter 4, you still should probably come in and ask a few more questions. All right, have a good one.